Okay, so we'll continue with regular sets and deterministic finite automata. Can you see my screen? Can someone confirm?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So as we saw, DFAs were, we had this mathematical modeling where we said that this could be thought of, let's say I write it as M equal to Q sigma S. Okay, so let me maintain the ordering. Delta S F, where Q was the set of states, sigma was the set of input symbols, delta, so this was the alphabet set, delta was the transition function. We mentioned that delta is going to be a function which represents, so basically you take q and some, for every q and for every symbol in sigma, you get state q. It could be the, so if you had q comma a, you delta of q comma a would be some, let's say p, where p could be equal to q, may not be equal to q, but this is a function. So for every q and a, you will have some next state defined with the transition function delta. We also specified that there's going to be one unique start state for these kind of machine models. There's going, for each such DFA, there's going to be a unique start state and a set of final states. The significance of these final states was that if I start at this, so I'm given a string as a sequence of alphabets, as a sequence of alphabets, and if I start from the start state and at every step I follow my transition function to go to the next state, at the end of reading the string, the input string, if I end up in a final state, then I will say that the machine, this particular machine, has accepted the input string. If not, then I say this machine has rejected the input string. So this was the meaning of this tuple. And we discussed some examples of some specific problems that were being solved by machines which were DFAs. And we also had a brief discussion to say that there is enough evidence to show that DFAs cannot accept all possible problems, languages or equivalently cannot solve all possible problems. Later on, we will also see specific examples where we construct languages which cannot have a DFA accepting it. What were regular sets? A language is going to be called a regular set if there exists a DFA, let's call it M, such that the language accepted by M is equal to L. So a particular language, if it's a regular set, it has at least one DFA which accepts this language. The language of the DFA is exactly this particular language. But it does not have to be a unique DFA. There could be many such DFAs which are accepting the same language. And because it's not necessary, somebody asked the question towards the end of the class, it's not necessary that every language has such a DFA. So every language need not be a regular set. We will see evidence later on. Now we saw some simple examples of regular sets. Now we are going to be looking at more complex languages where we can design DFAs and show that these languages are actually regular sets. So let's start with one such example. Here, I want to consider the set of binary strings, meaning over the alphabet 0, 1. I want to consider the language which contains exactly the set of binary strings that are divisible by 3. What do I mean by binary strings divisible by 3? So suppose you have a string, binary string x, consider the decimal number which this binary string represents, that should be divisible by 3. Okay, and you can assume that we are reading x from the leftmost bit. So the machine, the first alphabet that the machine is reading is the leftmost bit. So this is the problem. Now we want to see whether this particular language, which contains binary strings such that their decimal representations are divisible by 3, whether this language is a regular set or not. So previously, all the examples that we have seen, we've sort of tried to exploit the structure of the strings that are in that particular language. For example, whether the string has at least two consecutive A's, whether the string has a substring of the form BAAB, or whether it has a subsequence of the form BAAB. All the problems we saw somehow had some structural property of the strings that we were trying to exploit through in the design of the DFS. But here, if you expand the numbers that are divisible by 3, so for example, 0 will be written as 0, then 3 will be written as 1 1 as its binary representation, 6 as 1 1 0, 9 as 1 0 0 1. So there doesn't seem to be any particular structure in the string itself. In the set of strings itself, there is no common structure that we can exploit. Currently, at least we don't see anything like that. So then how else can we discretize the problem? Because see, the motive of these mathematical models is how can we discretize the problem? There can be something which is very complicated. Which are the parameters that we want to find out? Which are the parameters that we want to extract, which can themselves define this particular problem or this particular set of strings which forms the language? So what are the other things which can define this particular language? In order to do that, let's look at the string in terms of the numbers as well. So I'm going to denote, so if my binary string is y, then by hash y, I'm going to denote the decimal number corresponding to this binary string. So suppose we read one more string to the right. We start from the leftmost bit. Suppose we read one more bit to the right. Then what happens to this decimal number? So we should try and see what happens for what is the relation between the decimal number for y and the decimal number when I have read one more bit after y. So notice that if I consider the string x0, meaning 0 is just the symbol 0 is concatenated after x, then the number that x0 represents is just 2 times the number that the string x represents plus 0. Similarly, if I look at the string x1, where 1 is just concatenated after x, then the decimal number representing this or the decimal number that is represented by this is 2 times number represented by x plus 1. So in short, we can say that hash xc, look at the string xc where c can be any symbol from the alphabet. Hash xc or the decimal number represented by xc is going to be 2 times the number represented by x plus c. Okay. Now what happens if I now consider if I apply the mod 3 function on these numbers, because this is the final objective of this particular language. So how does the mod 3 function act? If I consider the new string hash xc, then this will be equivalent to 2 hash x plus c mod 3. Right? So if this is what the relation is, the mod 3 function is just going to be applied to the right hand side. Just for convenience, notice that when we consider binary strings, epsilon should also be considered. So just for convenience, this particular corner case where we have to assign a decimal number to this empty string, we will say that the number assigned to epsilon is 0. So 0, the decimal number 0 has 2 binary representations. Just for simplicity, you will see where the simplicity is coming. Just for simplicity, 0, the decimal number 0 is assigned two binary strings, the empty string as well as the string 0. Okay. So now one possible DFA construction could be that if I consider the mod 3 function, then there are three possibilities for the value of that function. It is 0, 1 and 3. So for each such value, each such value could be represented by a state. So as I'm reading the string, I'm going to be changing the current, as I read the string, my current binary number that is being represented by the current substring that has already been read is changing, and the DFA will sort of try to the transition will sort of try to capture the change in the value of the mod 3 function when I have read an extra bit. The transition will capture the change in the decimal number once an extra bit has been read under once mod 3 function has been applied. So if we, in the machine model, if we start, we can think that we are starting with the empty string and then we read the alphabets one by one. And since in our assumption we have that epsilon, the string epsilon represents 0, decimal number 0, then we can say that 0 is the start state. These are just this is a possible DFA that we can have. Okay. Now, by the problem that we want to solve, we require that the 0 should also, if we are considering this possible construction where a state represents a value of the mod 3 function, then the 0 state should also be the final state, because we want to only accept those strings that are that represent decimal numbers of the form 0 mod 3. Okay, so what does this actually mean? We saw that for any string, any binary string, hash xc is equal to 2 times hash x plus c, and this also meant if I apply the mod 3 function, hash xc is equivalent to 2 times hash x plus c mod 3. Okay, but we also know from the properties of the mod function that this can also be written as 2 times hash x mod 3 plus c mod 3, right? So this will be the same. These two things will be the same. So basically what this is telling us is, look at whatever value so if this possible DFA construction is correct, then if you look at however much I have read, the substring that I have read so far, if you consider the decimal number corresponding to that particular substring and take the mod 3 value for that decimal number, the possible DFA construction and the objective of the possible DFA function should be that at this point of time, I will be in a state that represents that particular value, hash x mod 3.
Ma'am?
Yes?
Should it be 2 hash mod 3 or 2 times hash x mod 3?
Where?
Ma'am, you wrote that 2 hash x plus c mod 3 as 2 times hash x mod 3 plus c mod 3, right? So should it
This
be?
whole thing? Mod
Yes,
3.
ma'am. I'm saying that 2 hash mod 3, we shall write 2 hash x mod 3 on a whole.
No, this is also true. Whatever I have written is also true. So you can work this out. If I take this particular number, I take, okay, I will not say also true. Whatever I have written is true. Can somebody prove this? I think you have done
A times
this
B
in.
mod X. We can use that. AB mod X is equal to A mod X into B mod X. I think that will work.
And after that?
A plus B mod C is A mod C plus B mod C.
Okay.
These two.
So just apply these two things, you will get this. You have done mod functions in discrete math, right?
Yes, ma'am. What you are saying is correct, and what he is saying is also correct.
So I think is this what you were initially saying?
No, ma'am, it is fine.
This is not correct.
No, ma'am, it is not.
Okay. Okay, so this is equivalent to 2 hash x mod 3 plus c whole mod 3. Yeah, okay, 1 minute. What was I trying to say? Okay. So what does this mean? Here, what we are trying to capture over here is that so far I have read the string x, and this is representing the number hash x. And if so what I want to do in my DFA construction, what I want from the states of this DFA is that whenever I'm doing a transition, at every stage, however much I have read of the input string, so far I have read a substring, then the number that is represented by this substring, apply the mod 3 function on this particular number. After I have read the substring in the DFA, I should be in the state that is represented by that value. This is what I basically want from the DFA, right? From the idea that we want to capture in this particular DFA is that whatever I have read so far, consider the corresponding number, consider its mod 3 value. The DFA should be currently in the state corresponding to that value. So now, if I add another, if I read one more bit, then that would mean that currently, whatever state I am in, let's call it Q, I should be going to the state 2Q plus C, whatever that value is, mod 3. Intuitively, this is what seems to be working for the construction we are trying to make. We are trying to capture that each state will represent what is the mod 3 value of the number corresponding to the substring read so far. And for that, it seems that intuitively it seems that if we define the transition function to be delta QC is equal to 2Q plus C mod 3, this should be capturing what we want from this DFA construction. Because of this particular property, that 2 hash x plus C mod 3 can also be rewritten as 2 of hash x mod 3 plus C mod 3. And this hash x mod 3 represents the mod 3 value of the number corresponding to hash x. So delta QC should be going to the value, should be going to the state from to the state 2Q plus C mod 3 from the state Q. So if I look at the transition diagram that captures this idea, that where the states, there are 3 states corresponding to 0 mod 3, 1 mod 3 and 2 mod 3. We want to accept those strings which are those strings whose decimal representation has decimal representation mod 3 is 0. So the 0 mod 3 state should be our final state. And the delta function, the transition function that we are proposing, just by the intuition of how the machine should work, is delta QC equal to 2Q plus C mod 3. Now, if you just work this out, so if you put q to be 0 and now you look at delta q, let's put c to be 0, then delta qc is just going to delta qc, if you look at the right hand side, 2q plus c mod 3, this is going to be 0 again. So if I am at 0 and I read the alphabet 0, I stay in the same state. If I am at 1, work out the right hand side, you will see that I go to state 1. And so on. So this is the transition diagram when I fix my start state to be 0. By our intuition, I want the final, the start state to be 0. I want my final, the set of final states to just contain 0 as its 0 in the set. And each of the states is basically each value for the mod 3 function. So what remains to be proved is, what is this delta QC function doing? Is it actually capturing what we want to do? So in order to see that, we of course have to look at the multi-step transition function, the delta hat that we are building from delta. And the statement is that since 0 is the start state we are fixing, delta hat 0x is equal to hash x mod 3. If we can show this, then we are done, right? Because in that case, look at the strings that are being accepted by the machine. They must be accepted, then delta hat 0 of that x will be equal to 0 mod 3. And then that means hash x mod 3 is equal to 0. So this is the statement that we want to prove. If we prove this, then this will lead to the fact that our construction is correct and we are actually accepting only those strings which are binary representations of numbers divisible by 3. And the proof again is by induction on the length of x. So in the base case, you take x to be epsilon. From the definition, recall the inductive definition of delta hat. Delta hat 0 epsilon, if I read the empty string, is going to, the DFA is going to stay in the same state. So we stay in the same state, 0. And now by assumption, 0 is also represented, 0 is the decimal representation of the epsilon string, the empty string. So 0 can be written as hash of epsilon, and therefore we can, since this is 0, we can write this as hash of epsilon mod 3. So in the base case, it holds that delta hat 0x is equal to 0 mod is equal to hash x mod 3. Now in the induction step, suppose this is true for, okay, this is true for all x, let's say of length I. Okay, so suppose this is true for all x of length I, and we want to show, okay, let me not say it in this way. So in the induction step, you consider strings of length I plus 1. Okay, and suppose it is true for all x of length I. Now you consider any string of length I plus 1, let's call it y, and let's say y is equal to xc. Now I know that the induction hypothesis is true for the string x. I have just concatenated an extra alphabet c to get this string y. So I want to show I have to show in this step that delta hat 0 y is equal to hash y mod 3. This is what I have to show. Okay, so then I write y as xc and I proceed. So on the left hand side, delta hat 0 xc is equal to delta of delta hat 0 x comma c. This is just the inductive definition of the multi-step function delta hat. Now over here I can apply the induction hypothesis, this one, because x is a string of length at most I. The right hand side I rewrite as delta of hash x mod 3 comma c. Now, again, hash x mod 3, sorry, now we are using the definition of delta to write it as delta of hash x mod c, comma, so hash x mod 3 is a state. Delta of hash x mod 3 c is going to be 2 times hash x mod 3 plus c mod 3. So again, hash x mod 3 is going to be a state, right? Because this is a number, this is a decimal number, mod 3. So this is going to be a value from 0 to 2, 0 between 0, 1 and 2. So consider that value. Delta of hash x mod 3 comma c is well defined. We just write it as 2 hash x mod 3 plus c, and there will be a mod 3 again. This hash x mod 3, I have just brought it down. So this was the q, let's say. If I wrote this as q, delta qc was 2q plus c mod 3. Q was taken as hash x mod 3. Now again, this is the property that we discussed earlier. 2 hash, this is equivalent to 2 hash x plus 3 plus c mod 3. Now we have also seen by the properties of the string x and an extra alphabet from 0 and 1 concatenated with x, that 2 hash x plus c mod 3 is same as hash of xc mod 3. Because hash xc is same as 2 hash x plus c. So therefore, we started with delta hat 0y, which is same as delta hat 0xc in the current assumption. And we ended with showing that this is equal to hash xc mod 3, which is equal to hash of y mod 3. We were taking any y of length I plus 1. So therefore, for any string of length I plus 1, we have shown that this statement is true. And therefore, we have proven the induction step. Okay, so any questions so far? We saw an example we took the example of a language which contains of only those binary strings that represent decimal numbers divisible by 3. And we saw that even this language is a regular set because we displayed a DFA for it.
Ma'am, I did not get what is the simplicity on using this epsilon as 0, hash epsilon as 0. Hash epsilon.
So there were several places where we used it. Let me just go back. So one place, so just to start off, we can think of, just to have an intuition of how we start off the string, we can think of the string as a sequence of alphabets. And therefore we can think, so suppose it is x1, x2, xn. Without worrying about what x1 is, we can always think of the first alphabet as epsilon, right? Because if x is equal to x1, x2 till xn, we can just concatenate. So this is same as epsilon concatenated with x, right? So we can think of the first alphabet of x as epsilon itself. This sort of gave us an intuition of what we want as a start state. Because epsilon, we said by our assumption, epsilon was corresponding to, epsilon can be thought of as a representation of the decimal number 0. So therefore 0 mod 3 is going to be 0. So therefore we can say that no matter what string it is, I can start from from the 0 state. Because now it is not just a pattern, right? We are sort of trying to capture the structure of a function, this mod 3 function. So therefore, these states mean certain things for that particular function. So even to determine what is a start state was not very intuitive. So one way of doing that was, I don't care what my first alphabet is for my string, for my input string. I think of my string as epsilon concatenated with the other non-trivial alphabets. And therefore, since I'm starting, since I am assuming that my first alphabet is epsilon, I can assume that I am starting with a portion. So at every stage, we are considering the decimal number of the substring read so far. So we can think that we are always going to start with the substring that corresponds to the value 0.
Yes, ma'am, got it.
Okay, another place, this is one way where this led us towards the construction. Another place where we are concretely using it is this. So in the base case, we are considering that we are starting off with the string epsilon, and we are, since hash epsilon represents 0, we are able to prove this base case easily without considering what is happening for each of the alphabets, etc. This was a clean proof for the base case. Okay, was I able to answer your
Here,
question?
what have we tried to prove?
We just, so what are we trying to show over here? Notice this statement. We are saying, so we defined so far, we have said, okay, this is my set of states. In the previous slide, we said that this is my set of states 0, 1, 2. I want my states to represent the values of mod 3. I want my start state to be 0 for a particular reason, because just to simplify, we think of the strings to be starting off with epsilon, and therefore I want my start state to start off with 0. I want my final state to be 0 because that's the definition of the problem. I want only those strings that are that have whose decimal number is divisible by 3. That's why I want a single final state to be that particular state 0. And with our intuition, we said that delta QC is equal to 2Q plus C mod 3. Now we still have to prove that we are accepting the correct language. So we have only intuitively decided what to do with one step, because we are reading from X, we are reading one more alphabet and considering XC, and we know the relation between hash X and hash X and hash XC, because we know this relation between the strings and their corresponding numbers. Therefore, the delta intuitively we could define. But what happens to the delta hat? What happens if I go multiple steps? So the statement we are saying of delta hat is, if I start from the proposed start state 0, and I read the input string X, this multi-step transition function delta hat should end up so delta hat 0 X means where am I ending up after reading the entire string X. It should end up exactly in the state which corresponds to the value hash X mod 3. So notice that if I do this, then in particular, if I consider those X's, so X such that hash X is equal to 0 mod 3, I will actually end up, so these are the strings that I want accepted, right? L is equal to X such that hash X is equal to mod 3. This is the language I want to accept. Then notice that delta hat 0x is equal to 0 mod 3. So we are exactly landing, for those strings that are in the language, we are exactly landing up in the state we want, in the
here you
final
are saying
state.
that such X such that hash X mod 3 equal to 0. Are you meaning this word?
Huh?
Sir, ma'am, you are writing here that
So
hash X equal to 0 mod 3.
how do you write it? So this is how I write my mod function. Hash X is equal to, so some number, let's say A is equal to value mod 3. So something like A is equal to B mod 3.
Or should we write it like Q mod 3 equal to B?
Okay, so when I say hash X is equal to 0 mod 3, I mean that look at hash X divisible by 3, the remainder is 0.
Okay.
So when I say A is equivalent to B mod 3, I mean that if I divide A by 3, the remainder is B. The remainder is, okay. So here
B.
what I mean is, you divide A by 3 and you divide B by 3, the remainders will be the same.
Okay.
Okay, so what did I mean by this statement? Is it clear now? So what I want to prove is, look at the state that I'm landing up at. When I start from the start state and I've read the entire string X, I should be ending up exactly in the state which is, you consider the decimal number corresponding to hash X divided by 3. Look at the remainder. That remainder can be between the values 0, 1 and 2. So the state, and we also have states 0, 1 and 2. The state that we end up in should be exactly that remainder value.
Yes, ma'am.
And in particular, this also proves, if I can prove this particular statement, I have also proven that the language we are accepting, so since 0 is the, okay, there are two ways. Let us go through in each direction. In one direction, we are showing that if you consider those, if you consider this particular language X such that hash X is equal to 0 mod 3, meaning that if you divide if you divide hash X by 3, you get the remainder as 0. Then you know that if I do this, I'm going to land up in the state 0, which is my final state. So all strings in the language are definitely getting accepted. Now look at any other string. So any other string is going to have value something else, right? If you look at any other string that is not landing, so if you look at the other strings in sigma star, if you look at sigma star minus L, then this consists of X such that hash X is equivalent to 1 mod 3
Or 2
union
mod 3.
X such that hash X is equivalent to 2 mod 3. So by this statement, we know that this set is going to land up in the state 1 and this set is going to land up in the state 2. So sigma star minus L is not getting accepted by this DFA. Therefore, if we can show this particular statement, we have proven that the language that is being accepted by the DFA we constructed is exactly the language divisible by the language consisting of strings whose decimal numbers are divisible by 3.
Okay,
Okay.
ma'am. Yes.
Ma'am,
Any other questions? Yes.
suppose we are giving given an English language description of a problem, and we have to check whether it is a regular set or not. Then
Yeah.
do we have to explicitly find delta hat for this, or if we can find a transition state diagram, then we are done.
But how will you show? You have to still prove that this transition state diagram is correct. So for example, we had a transition state diagram a while back, but we don't know whether this is going to work or not. You have to formally prove that this works, right?
So a DFA is defined by delta, right? Delta hat is.
Correct.
Then why we are trying to prove things about delta hat?
Because we are trying to prove things about delta hat, because if you consider the language accepted by the DFA, suppose the DFA is M, the language accepted by the DFA is all X such that delta hat SX belongs to the final state. That's the reason why we are interested in delta hat.
Okay, ma'am, understood.
Any more questions? Otherwise, I'll move forward.
Ma'am, why were we accepting null string as a valid, as a accepted output? Like,
Null string could be an input, right?
yeah, so why is it accepted? Like, for that, modulus isn't even defined.
Yeah, so just to handle that case, just to handle the case, what should we do with the null string? The null string does not have any meaning in the actual, in the decimal world, right? But the null string exists in terms of how DFAs are defined, the null string exists. So we have to handle the null string. Either we could have rejected it. This is like a corner case. Either we could have rejected it or we could have accepted it. It does not really make a difference.
Okay, so,
So
both of the cases are
because
correct, right?
yeah, sure. Both cases are correct, but for this particular construction, we have assumed that the null string will be accepted.
Okay.
Because we are assuming that the null string also represents 0. So we are not accepting any random decimal number. We are just saying 0 is represented by the null string as well as 0. We could have, it is possible, if you took the assumption saying that epsilon does not represent anything meaningful in the decimal system. So I want to, if epsilon comes, I want to reject it. Then you should have designed something separately. But here what we saw is it's easier. There are certain places where it's becoming easier if I just make this one particular assumption that epsilon will be accepted, because epsilon we are taking as 0. In this particular example, it works because 0 is actually divisible by 3. So we made this particular corner case work for us so that we have a simple DFA and we have a simpler proof.
Okay, understood.
Ma'am, how are we deciding the start state in this problem? Like that is our assumption, like that epsilon means it is making simpler calculation. It is enabling simpler calculations. That is the reason we are taking 0 as the start state.
So a priori, I can't see what to take as a start state, right? Because we just said a state will represent a value for, a state will represent the value, a value of mod 3. Now, if I forget epsilon for now, that means this is a non-empty string. So that means I have some x1, x2 and so on. So the first alphabet is going to come from 0 or 1. Right? So 0, the numbers, and we also must keep what we are trying to construct. We are trying to capture the fact that at any point of time, I will be at a state that represents the remainder value of this particular number corresponding to the substring I've read so far. So I have read so far, let's say x, this corresponds to a number hash x. Look at the remainder, that will be some value from 0, C coming from 0, 1, 2, and I should be at this state C. This is what we want to capture. This is how we are trying to construct the DFA. If you considered some other DFA, of course, you will be doing it differently. The basis of all these things is the fact that I am saying I want to capture my states as these the remainder values of the decimal number read so far. So then if I consider x1, it could be 0 or 1. So now what naturally I don't see a natural unique start state. We have to have a natural unique start state, right? I don't see a natural unique start state. So how we made this work for us is we consider x to be epsilon concatenated with x1, x2, etc. Now epsilon, it can be rejected, it can be accepted, it doesn't really matter. So what we did is we accepted epsilon by saying that it actually represents 0, the decimal number 0. And then I have a unique start state to define. I have a unique start state that I can define.
Okay, ma'am, understood.
Okay.
Ma'am, can you go to the transition diagram?
Transition diagram, yeah.
Ma'am, here at the 2 mod 2, if a 0 comes, should it be at 2 mod 2 or go to 1 mod 3?
Okay, maybe I have made a mistake here. Let's see. So you're saying 2 and what is this? 2. 2 and what is the alphabet?
1.
2, 1. So this is plus 1, 5. It stays in 2, right? This is 5 mod 3. I did not understand your question then.
Ma'am, here, if it is 2 mod 3, then we have in string and binary representation, it is 1, 0.
2 mod 3 is 1, 0. I mean, if the string is 1, 0, then my number currently is 2. And then this is a special case of 2 mod 3. But I can have different strings. Currently, I could have read, my input string read so far could be some other number, which is 2 mod, which when divided by 3 has remainder 2.
Yes, ma'am. For now, if we take 1, 0 and we get 0 again.
1,
Sorry,
0, and then I put 0 again.
yes, ma'am, it is fine.
It's fine, right? Okay. Okay, can I move on or any other questions? Okay, so now let's construct some more regular sets. Let's see what we can do. Suppose I have two regular sets. Suppose I know that I have two regular sets. Then a natural question to ask is, we saw certain relations between sets, right? We saw a union, we saw the union operator, we saw intersection operator, complement of a set, and then concatenation of two sets, or like a star, which is multiple concatenations. So what happens if I know that A and B are regular sets, meaning that A is accepted, there exists a DFA that accepts A, and there exists some other DFA that accepts B, then what happens to the union? Is that also a regular set? This seems like a natural question to ask. So in this class, we will be looking at these three examples. Concatenation, these two concatenation examples as well as A plus, we will be seeing later in a later class. Probably next class, but I can't remember now. But we'll be seeing it later after we know some more details. Complement already last class, one of you had answered. What do I do if I want to design a DFA? Suppose I have a DFA for A. What do I have to do to design a DFA for the complement? I just I keep the same states, same set of states, same start state, same transition function. Only the set of final states will be all the previous non-final states. So now if I was accepting a string in the DFA for A, I will be exactly rejecting that string in the DFA for not of A. And if I was rejecting a string in the DFA for A, I will be accepting it in the DFA for not of A. So this you had answered. Now let's look at whether we can conclude for the intersection operation and the union operation. So for the intersection operation, so suppose A and B are two regular sets. That means that there is a DFA M1 that accepts this particular language A and a DFA M2 accepting the language B. Now, can I design a DFA for the set A intersection B? So what is the intuition for this? If I have to accept it, notice that in M1, because this is a DFA, in M1, there is a unique path, unique directed path starting from the start state that is labeled by, so suppose, let's say my string is X, which is, let's say, C1, C2, C3, C4. Let's just assume one particular example. If I want X to be in A intersection B, I know that X must be accepted by M1 as well as M2, which means that look at the unique path in M1 that is labeled by X, meaning labeled by C1, C2, C3, C4, starting from S. Since X is in M1, that means the final state is, the ending state is a final state in M1. Since X is in M2, you consider the unique path labeled starting from the start state of M2 and labeled by X. Look at the ending state. That must also be final state. Only then will X be will be in A intersection B. Correct? So there is a unique, for any string X, there is a unique string in M1 that is starting from the start state. If the unique string ends in a final state, that means that that X is being accepted by M1. Similarly for X being accepted by M2. So if X has to be accepted, if X has to be in A intersection B, that means the unique path starting from each of the start states of M1 and of the respective start states of M1 and M2, look at the unique path labeled by X, they must be ending in final states of M1 and M2 respectively. So now this is the intuition. This is what we have to do. Now we have to design a DFA that captures this particular structure of M1 and M2. So this has a name, this particular construction has a name which is called the product construction. And basically what we do is we define this new DFA M3 this, which is corresponding to this tuple Q3 sigma. Sigma remains the same because I am accepting strings which are in A as well as in B. If A and B are over the alphabet sigma, then A intersection B is also the same. Then the transition function delta 3, some start state S3 and final states F3. Now what are these states? What I can think of a state in this new DFA M3 as a product of the so I can think of the set of states as a product of the set of states of M1 and the set of states of M2. So a particular state in M3 can be of the form Q1, Q2, where Q1 is coming from Q1 and Q2 is coming from Q2. So a start state S3 will be S1, this will be S1 comma S3, S1 comma S2. The set of final states, now again notice that we want only those strings where the string is ending up in final states in both M1 and M2. So the set of final states should be F1 cross F2. So a final state in M3 will be some F1, F2 such that F1 belongs to F1 and F2 belongs to F2. Okay. And the transition function for a particular state PQ on reading A should behave in such a way that as if delta 1 is the transition function for M1, delta 1 is acting on P on reading A, and in the second part delta 2 is acting on Q on reading A. So we are sort of capturing this two DFA structure by saying that, okay, why don't I have to capture these things simultaneously, right? I have to capture that from the start state C1 is moving to a particular state in M1 and a particular state in M2. Why don't I capture these two states as one state of the new DFA? And why don't I consider this transition? So I start with these two states corresponding to the start state of my new DFA. So these two states corresponding to the start state of my new DFA, and let's say on reading C1 I will go to these two states. Then why don't I define my transition function as if the first component defines what is happening in M1 and the second component defines what happens in M2. Okay. So this is called the product automaton. M3 will be called the product automaton of M1 and M2. So now we have to again define, since we have to prove that M3, the language accepted by this new automaton M3 is actually A intersection B, we have to prove something about the multi-step transition function, because ultimately we have to show that this language, let's call it L of M3, this I know is X such that delta 3 hat S1, S2, X belongs to F1 cross F2. This is what I have to show. This is what the accepted set of strings is. I have to show that this is equal to A intersection B, which basically is L of M1 intersection L of M2. So this is what I have to show finally. So then I have to understand what the multi-step transition function is doing. So here, please prove this for yourself. Try to prove it for yourself. It's again, okay, no, let me inductively define it first. The inductive definition of delta hat 3 will be delta hat PQ. PQ is a state. On reading epsilon, it will just remain in PQ as per the definition of a multi-step transition function. And the inductive inductive part of the definition is delta 3 hat at a particular state PQ on reading XA is same as delta 3 of delta 3 hat PQX comma A. Okay, now we want to show that no matter what input string I have, delta hat PQX is equal to delta 1 hat PX comma delta 2 hat QX, meaning that no matter where I am, in my new DFA, wherever I am, if you look at wherever I am, if I look at the path labeled by X from this particular state, let's call this PQ, and suppose I'm ending at something, P dash Q dash, and this path is labeled by X, then what M3 is doing, suppose this is in M3, then this is same as if I looked at P, look at the unique path labeled by X from P, this should land at P dash, and Q, look at the unique path labeled by Q, so this is in M1, this should land in Q dash in M2. So this multi-step function delta 3 hat is actually behaving as if delta 1 hat and delta 2 hat are acting on X. Delta 1 hat and delta 2 hat are taking in X as input. So in order to prove this lemma, you have to again induct on X, on the length of X. I will leave this proof. It is in the slides, but try to prove it on your own. Similar strategy. Once we prove this particular fact that delta hat 3 PQX, so delta hat 3 PQX is equal to delta hat 1 PX, comma delta hat 2 QX. So in particular, this also implies delta hat 3. If I started from S1, S2 on X, this would mean that I have delta hat 1 S1 X, comma delta hat 2 S2 X as my ending state. Okay, so now let's look at all the languages, all the strings that are being accepted. So what we will prove is LM3 is exactly equal to LM1 intersection LM2. LM1 was A, LM2 was B, so LM3 is exactly A intersection B. So here is the proof. X belongs to LM3 means that delta hat 3 starting from the start state, reading X will end up in a final state of M3. This means that delta hat 3, the start state was S1, S2, comma X belongs to F3. Now delta hat, by definition of delta hat 3 and using lemma 1, I can rewrite this as delta hat 1 acting on S1 on reading X, comma delta hat 2 acting on S2 on reading X. This should finally end up in F3. Now what does F3 mean? The definition of F3 was F1 cross F2, which separately means that delta hat 1 S1X belongs to F1, and this is just how. So if I say Q1 comma Q2 belongs to, let's say, Q1 cross Q2, that means the first thing belongs to Q1 and the second component belongs to Q2. So we are just using that to say that delta hat 1 S1X belongs to F1 and delta hat 2 S2X belongs to F2. Then this means delta hat 1 S1X belongs to F1 means X belongs to M1. This means that X belongs to LM1. And this means that X belongs to LM2. And this then finally means that X belongs to LM1 intersection LM2, which is A intersection B. Any questions?
Ma'am, this proves that LM3 is a subset of LM1 intersection LM2.
Why?
We need to prove in both directions, right?
So
Like
okay,
equality of-
these are all both directions. I'm exactly using definitions.
Means the word means bidirectional implication.
Bidirectional. This is okay. Maybe I shouldn't have used means. This is exactly this.
Okay, ma'am.
Because everywhere I'm using definitions or lemmas, right?
Okay, ma'am.
Ma'am, so does that mean it will hold true for union also?
Can you tell me, will it hold true for union?
Ma'am, I think it will hold true because it is
Right.
the intersection of three sets like A union B is A intersection B, intersection A not B. And
Wait,
then,
wait, wait. A intersection B intersection. No.
yes, ma'am.
A intersection B could be much smaller than A union B. Just
No,
by
no.
cardinality, this is not true.
Intersection A naught, intersection B.
What is A naught?
Oh, sorry. I think it is wrong. No, it will not happen.
A intersection B can be much smaller than A union B. How can the right hand side, just by cardinality, this is not true. But I mean, is there any other way? Do you know of any other way of relating A union B with A intersection B, or something, some related A
A
B?
complement intersection B complement the whole complement.
So you're saying this is not A intersection not B.
Yes.
So now can you? So what is the answer? Is A union B a regular set? If A and B are regular sets?
Yes, ma'am.
Yes, ma'am.
Yeah. So we are done. It is closed. So DFAs are closed under union. By De Morgan's law, A union B is not of A intersection not of B. So what do? We first construct DFAs for not A and not B. Next step, we do the product construction for not A and not B. So that means it is accepting a language C, which is equal to not A intersection not B. And then finally, we just have to construct the DFA for not C in order to accept A union B. Can you tell me intuitively, can you tell me what the, so suppose, can you tell me what the states, start states,
Ma'am?
final states are going to be?
Ma'am, can we not construct an entirely different automata which is similar to the product automata,
Yeah.
but the final states are not F1 plus F2, but anything that has S1 as the, like, anything that has the first argument from F1 union anything that has the second argument from F2.
Okay, so you're saying let us take F3 to be F1 cross Q2 union
Q1 cross F2.
Q1 cross F2. Yeah.
Yes, ma'am.
So basically it will be same as the product construction, because what are we doing? Again, if I look at the M1 and M2 separately, if you look at X, the path starting from the start state of M1 and labeled by X, since it's a DFA, it's going to be a unique path. Look at the end point. Look at the end state. Similarly, look at X in M2 and look at the end state. If X has to be accepted in A union B, or if it has to be, if X is in A union B, at least one of these two things must be, let me not do this. At least one of these two end states must be a final state. So this is what is being captured. Now, how do you capture this? Like I'm doing something in M1 and I'm doing something in M2. How do you capture this? Something similar to the product construction, where you take the Q3 to be again Q1 cross Q2, and the rest I think you should be able to work out. Actually, what you're saying, the exact thing will come out if you do this 3-step construction.
Yes, ma'am, that has to happen because we are not changing anything other than that final state and the set of states.
Yeah. So the product construction, the direct product construction that you're doing sort of takes care of these first 2 steps. Okay, so that is all I have to say today. Any questions so far? Okay, then so we had a look at DFAs. We will be looking at we will be looking at another kind of finite automata, which we will be calling non-deterministic finite automata. So in the beginning, when I define it, it will seem like it's a generalization of deterministic finite automata. But then we will see that actually it's not a generalization. NFA, the set of NFAs or the set of problems that can be solved by non-deterministic finite automata are exactly the same as a set of problems that can be solved by deterministic finite automata. So we will see what non-determinism means and how this generalization happens. And then we will see that this is actually, by definition, it seems like it's a generalization. We relax certain things, but actually it does not give any extra power to this non-deterministic finite automata model. And DFAs have exactly the same power as NFAs. This we will see tomorrow. Okay, thank you.
Ma'am, the start state for A union B is S1, S2, right?
Start state is S1, S2. Yes. Are there any other questions? Otherwise, I will end the meeting.